So we're known a lot for what we do on helicopters, but again, 5-minute commercial on what we do. We've been in business for about 30 years, and our niche is aerodynamic products on helicopters and airplanes, and that's just a laundry list of the things that we've worked on and developed and certified over our history. The business was started in 1992. Where does BLR come from? The company was originally called Boundary Layer Research. In 2004, a new ownership structure was developed, and the business BLR Aerospace was formed. We've got over 100 STCs. We're not a big business from an employee point of view. We only have 23 full-time employees. We've got a bunch of DERs and consultants that help us. We don't make anything. We don't manufacture stuff. We focus on developing products, flight testing, getting them certified. We live in an area where there's lots and lots of aerospace suppliers, so there's no point in us making our own stuff. We just buy the stuff we need, bring it in, inspect it, inventory it, kit it up, and then ship it out and supply technical support all over the world for installations. And we're one of the things we've gotten good at, in my humble opinion, is certification management and flight testing, and that's what, again, Dan and his team have a big contribution in, and that's really our core competence. If it wasn't for the FAA, we would have twice as many products. This is just our portfolio of stuff we've done over time. We developed winglet systems for a couple of the Beechcraft King Air models. We've got we're the distributor exclusively around the world for a product made in Germany called the MT Whisper prop. It's a 5-bladed composite prop that we bundle up with our King Air winglets and sell it as a performance bundle. We've developed FastFin systems for all the Bell Medium platforms, from the UH-1 to the 412. Recently, right behind you is the AH-1 Cobra. We'll talk more about that in some detail. And then we've also certified a FastFin system on the H-125. And we've been through a couple of iterations. We'll get into that a little bit. You guys know that. We've been through a performance upgrade with Airbus, and so that's another one of our products. And then just some older, we call them legacy products, which were the beginning of boundary layer research. These are 3 production contracts. All these products started as aftermarket products, and in all 3 cases, the OEMs decided, because of the contribution they make to the platform. In the case of Beechcraft, our winglet system is standard build in the factory, has been for 10 years. Our actual performance manual, our flight manual supplement, comes with every brand new aircraft because we certified improved performance. Ditto with the Bell 412. That started as an aftermarket upgrade. Bell is installing it in Mirabel on all new 412s. Subaru recently signed a license agreement with Bell to build 412s in Japan for the civilian and military fleets, and that's our system's going to be standard on that aircraft as well. And then last but not least, the 125. Airbus has now made that a optional factory upgrade available to all new aircraft, and we expect that that'll morph into more as the appetite for increased performance happens. So we've sold 1,000 winglet systems for King Airs. This is pardon me. We're going to talk about this more in detail after lunch, but we talk about our FastFin systems in 2 phases. What we call the first generation FastFin system, that's really the Bell 412 system. It's tail boom strakes and a modification to the fin. We got smarter over time and developed what we call the second generation FastFin system. That's what's here today. This is a modification where the boom goes from a symmetric shape, to an asymmetric shape. And there's reasons why that produces even bigger benefits than the first generation, and we'll get into those technical details after lunch. We've done a lot of work and spent a lot of time and energy patenting this, protecting this invention. And so far to date, knock on wood, we haven't been challenged in any of that. And today is Cobra and Blackhawk. And that's our other facility. That's in Gunnison, yeah? So it looks a lot like this, clean, tidy, with aircraft in it. And the meter's running from a cost point of view. So that's all we had to share, just to give you a commercial about us and a little bit more context in terms of what we do above and beyond just helicopter stuff.
So we start with a project-specific compliance plan. That drives what we have to flight test. That also drives what instrumentation is required to basically make those plots and show the FAA, this is our data, here are all the parameters that we got to be within, and we can show that for every data record that we've taken to substantiate our approvals. So that includes winds, which EASA currently doesn't have, and Airbus is having problems with EASA, but we have it live in our data stream. And also our data streams are sampling at over 2,000 samples a second. So we're taking 10 seconds of data. We have a ton of data that's empirical, both on engine systems that we tie into, flight control parameters, positions, strain gauging, weather coming into the aircraft. Everything that's involved with the certification effort is all in that data stream. And we can actually go out and do rapid prototyping in our early phases to develop what our product's going to be, and all of that is all in-house. So we'll take some time to show you like the position sensors on the Black Hawk and how the data system's set up. Usually we have 1 or 2 data systems. This aircraft has 2 data systems. So our core competency really can go as deep as we want. We use a National Instruments data system, which is all PC-based. And right there you can see all of the sensors coming into this main unit right here. So these, in this unit, all the control position, fuel flows, load cell, engine SDC data for both engines, and all of that. This will give you a little bit of an example of so this is all of our SDC tie-in, so all of the signal data converters that come in from the engines. We're all tapped into both 1 and 2 SDCs. Comes into matrix blocks and comes back out and goes to our data processing unit. So like this is our air data computer that's tied into the pedostatic systems. So we get real-time airspeed, density altitudes, pressure altitudes, and then of course all of our TGTs coming out of the engines are all tapped into. So everything we normally do for flight test, all the brackets are orange, wires orange, so it's easy identifiable as you go through the aircraft. So that alone is just the engine tie-in. So this SDC tie-in, you actually take all the connectors apart, D-pin, put pins in, put jumpers in. It takes about 2.5 days to do this. And that's all developed in-house. In the cockpit area, for the pilot side, we have a repeater monitor that's up front so the pilot can see the important parameters for the test. So what that gives us is control positions, V&E calculator, which I'll show you on this computer, and gives us all of the parameters when we go out to do specific tests. It gives me all that information. Also on this, I've got a downward looking camera when we're doing tethered hover that I switch it over, and I can actually spot where the line is, and I fly that off that position instead of hanging out the door. And then back here you can see the flight test engineer's position, which he has a surface just like this that is installed. So all of these are called virtual instruments, or VIs, that come off the National Instruments software. So all of these VIs can be customized for anything that you need displayed for the flight crew and the test crew. And there's also the associated warnings, whether we have a DAC failure, we have a caution that we set pre-limits on, saying, okay, we're not going to exceed so much strain on the tailboom. We can put caution and warnings to knock it off. GPS signal loss, weather station loss, and all those things. This column here, this is where all of our weather station, our ground weather station, comes in. So it gives us wind speed in knots, wind direction, OAT, and our pressure altitudes. For low speed control, we've got a 5 hertz GPS. It's independent. So it's a fast rate GPS. We don't use pace vehicles. We do it all off of GPS ground speed. It's just safer. We don't have to have a car and an aircraft on a runway with people getting off runways. It's just, we found that it is far easier for us to do that. Then we have load cell that displays in pounds and calibrated in pounds. Then also our air data computer, indicated airspeed and OAT from our air data computer. Down here we have engine torques and TGTs because we actually take a lot of hand notes. We've got written files for everything. So that's the core software that we use when we're doing flight test, and that gets repeated up on the pilot monitor also. So back here we've got, like I said, air data computers up front. AHRS and everything else is mounted on top of this bracket. And then all of the orange wiring heads back into the tail boom because we have strain gauges in the tail boom with another data control unit back there. We have 5 vibe sensors, which 3 of them are 3-axis, triaxial vibe sensors. And we've got 10 strain gauges, and then we've got another control position sensor on the impressed pitch up on the tail rotor gearbox. So we have strain gauges on the top and bottom stringers. We got strain gauges on stringer 5, 3, 5, 7, and 13 on both sides. And they're full Poisson half bridge strain gauges that are all sampled and temperature compensated that all go back into the DAC that's back in the tail boom here, which is our data acquisition unit. We also have, like I said, 5 vibe sensors, 1 at the front of the tail boom, 1 at the intermediate gearbox, 1 up the 90-degree gearbox, and then 2 on the horizontal stabilizer, which are unidirectional. So all of those are showing us both tension, compression on both sides of the booms as we're doing our maneuvers, steady heading side slips. So we used the same locations as the Army did and had pretty good correlation with all of those trends. So we're just making sure that we're not affecting the attach point of the tail boom, because that's usually where most of the problems are happening.
Story of how we actually got here. NASA developed some technology they called dual tail boom strakes. After the Vietnam War, a lot of UH-60 helicopters suffered from what's called loss of tail rotor effectiveness, and so after that experience, NASA was charged to try to figure out what could be done to improve that phenomenon. And they developed what they call dual tail boom strakes, which are stall strips on one side of the tail boom. And I'll talk more about what they actually do in a minute. So we licensed that technology from NASA and commercialized it on a bunch of different products, or platforms I should say. And first one was the UH-60. So we got that certification about 4 years later. And then we figured out the idea of carving out the back of the vertical fin on the Bell medium to reduce the amount of blockage. And we invented that, certified it in a few years later. And then fast forward a few years through some difficult times with Bell. In the end, they decided that our system helped their helicopter enough. They made it standard equipment, and we signed a long-term agreement with them. And that became what we call the first generation FastFin system. Beginning. The downwash from the main rotor rushes over the tail boom. The tail boom is curved on both sides. Bernoulli's principle says you're going to get negative pressure where you have those curved surfaces, and you get it on both sides of the tail boom. One pressure pushes the tail boom that direction, the other side pushes it that direction. They fight each other. What NASA figured out was putting stall strips on one side, the side that is working against the interest of the tail rotor, improve that. And they were right. That was a good idea. And they didn't have it exactly right. We fiddled with it and made it better. But the whole principle was spot on. It was, how do you harness the energy from that main rotor washing across these curved surfaces and make that tail boom actually help the tail rotor do its job? And this just shows what I was trying to describe. The main rotor washes down the tail boom. You get forces on both sides of the tail boom. One side is helping the tail rotor, one side is working against the tail rotor. When you put these stall strips on, then the side that's working against the tail rotor's interest go away. And now you actually have the tail boom pushing in the same direction the tail rotor is. In the same kind of vein, this big area represents blockage for the tail rotor. And when you remove that area which is in the way of the tail rotor and put it back down here so you maintain the weathercock stability you need from the fin, you get less blockage, you get a more efficient tail rotor. And the best way to depict this and understand it is to watch a video.
The FastFin system is an elegant, no-moving part solution to an inherent weakness seen in many early enclosed tailboom helicopter designs. Limited tail rotor authority, which significantly reduces the potential lifting capacity of a helicopter and may compromise safety margins in challenging operational conditions. The FastFin system incorporates 2 parallel stall strips along the left side of the tailboom and reshaped vertical fin. These modifications combine to optimize airflow around the tailboom. With FastFin installed, your bell medium can realize certified useful load increases up to 91%. And even more compelling, BLR's FastFin will all but eliminate the sudden and seemingly unpredictable loss of tail rotor effectiveness, known as LTE. How is this possible? The answer is aerodynamics. Studies by NASA and BLR reveal that rotor wash over the tailboom enclosure causes the tailboom to act much like a wing, creating adverse low pressure along the left side of the tailboom. This adverse low pressure works against the efforts of the tail rotor, causing the tail rotor to require higher thrust. NASA studies also show that the low pressure phenomenon is not a constant force. Kármán Street vortex shedding causes the low pressure to fluctuate continually, creating instability and requiring the pilot to constantly make corrections for yaw. This is, in fact, the phenomenon that makes helicopters so difficult to fly. Fluctuating air pressure shakes the tailboom left and right, and constant pilot corrections are necessary to achieve a steady and safe state of hover. By reducing required tail rotor pedal reversals up to 35%, BLR's FastFin system not only reduces the stress on the aircraft and pilot, it also increases the aircraft's safety performance in hover. In additional research, it was demonstrated that by installing stall strips, or strakes, on the left side of the tailboom, the low-pressure area acting on the tailboom is reduced, which in turn reduces the horsepower required by the tail rotor. Valuable energy can now be redirected to the main rotor, allowing for significant increases in useful load. The tail rotor produces anti-torque force by thrusting air sideways. Some of that air is driven into the vertical stabilizer, reducing overall efficiency. By relocating material away from the affected areas, FastFin has reduced energy loss while retaining weathercock stability in forward flight. By introducing a newly shaped trailing edge, which closely resembles the shape of the leading edge, dramatic increases in wind azimuth tolerance can be achieved. When both modifications are combined, the result is an incredible increase in tail rotor effectiveness during hover and in low-speed operations. Simply put, the easy-to-install FastFin system modernizes and improves the aircraft by optimizing the airflow through the tail rotor and over the tailboom, increasing tail rotor efficiency, which preserves precious engine horsepower for the main rotor and increases available yaw control to optimize the lifting capacity of the helicopter.
Anyway, the reason why the numbers are so big, why there's such a significant improvement or increase in performance, is because the Bell Medium fleet series has just got an anemic tail rotor. It just needs a lot of help, and so it finds itself tail rotor challenged or directionally control challenged in lots of environments, and we fix that in a big way. That's why Bell put it on as standard equipment in Mirabel. So this is a UH-60, and we actually did this work about 3 or 4 years ago when we were first talking to the Army. So that's a model of a UH-60. And then we modify it with these mathematical models to include our fairing on the one side and our strake on the other. We go as far as to add antennas and all the other idiosyncrasies that reflect what the real aircraft's configuration is. And then this is what the tool tells us. So this is called computational fluid dynamics. So these two plots here are the unmodified tailboom. You can tell that because it's just got that symmetric shape with the drive shaft cover. This is the modified tail boom that has our fairing on it. And you can see this little yellow area, that's where the strake is. So what these are pressure plots. So they're predictions of when the mass of air comes rushing over the tail boom. I said before, you get pressure on both sides of the tail boom when it's unmodified, fighting each other. Blue area represents a suction pressure, negative pressure. So on this side, that suction is pushing the boom that way. On this side, it's pushing the boom that way. And ditto, this is just different stations, further forward, further aft. And then when you change the shape, put a strake on, now you can see all the negative pressure on that side, for the most part, is gone. And there's more of it on this side. So this side is no longer pushing that way. It's not doing anything. And that's pushing that way. And that's the whole objective of this modification. This is the same data. Some engineers like to look at this in terms of the speed of the air. You know, a wing, high speed air over the top of the wing creates lift, creates negative pressure. This is showing that red is high speed air. It's the same phenomenon. You put a strake on this side and a fairing on that side. All the high speed air on this side goes away. It's all on that side. It's the same phenomenon. It's just shown in a different format. And then we've gone as far as to now take those two-dimensional plots and then consider that three-dimensionally, where you can look at the entire gradient up and down the boom. This is baseline. We're looking at the left-hand side of the tail boom. And you can see all that negative pressure that's pulling the boom out of the screen is now gone away with the modification. And then on the starboard side of the boom, the side of the boom that has the fairing on it, there was some pressure, negative pressure, and now there's a bunch more. So that's the whole end game, is to create that phenomenon where the boom becomes part of the anti-torque system. And what we are able to do is to now analytically calculate how much anti-torque the boom creates. In this example, it's over 5,000 foot-pounds of torque, and the engine creates about 55,000 foot-pounds of torque. So if the tail rotor is creating about 10% of the anti-torque, that means the tail rotor's got to brake 10%, and that saves you pedal margins. And when you do the math, you can calculate there's about 600 pounds of additional useful load based on the savings in the tail rotor energy. We're almost done. We've talked about that already. So I'm going to try to make sense out of this plot. So Dan talked about coefficients of power and coefficients of thrust. So you got all this data, and the data for hover performance is relating engine power and lift. In other words, for a certain amount of engine power, how much thrust, how much lift can you create? And the way we process all of our flight test data, and then determine how we can adjust the performance charts to reflect the improvement that our system creates, we develop these plots which relate power to lift. And one of the lines is the baseline helicopter, and one of the lines is the modified helicopter. And the split between them says that for the same power, I can have more lift than I could before. And what Dan was talking about earlier was that if you've got a flight test data point at 6,000 feet and 20 degrees centigrade, and then the next day you've got 8,000 feet, 30 degrees centigrade, this approach allows you to actually consider both of those points, because it takes out it considers the density altitude differences. And so analytically you can collect all this data at different altitudes and temperatures and then compare them to one another for performance calculation purposes. And the punchline for this aircraft is that in OGE hover, those 4 points are important to the Forest Service. That's why we use those as barometers of what the improvement is. So at those 4 different altitude and temperature combinations, there's anywhere from 400 to 600 pounds of additional useful load that we're going to certify for this aircraft. And the performance charts, hover charts, will expand out and reflect that additional useful load. And these numbers are net of the kit weight. The kit weight, the physical weight of the kit is about 35 pounds. So that 600 pounds is actually net of what the kit weighs. We got to be careful about what we talk about regarding the UH-60 M, but we entered into a CRADA with the Army in 2018. We did a flight test in 2020, and that's the system. It's that system on a mic. Vortex generators, it's exactly the same. We danced around this question about steel cables and Kevlar cables, and the data for this test wasn't as conclusive as for this. We're hoping that we find ourselves in a position to do another round of testing with the Army. That was the conclusion from their flight test report was more testing should be done to improve some of the things that didn't come out as well as we hoped because of some of the testing procedures, and there wasn't enough time to do as much testing as we would have hoped. But that system produced about 500 pounds of useful load on the M, and so that's got real value to that aircraft, just like this. And so I think that's it. Anything else we should say about that? And just one, I think just the last point I wanted to throw out is, any helicopter that's got an enclosed tailboat, this works on.